In this section, we talk about what to do if you're trying to find a confidence interval for the mean and you don't know the population standard deviation. And it's actually very, very similar. You just need to go to a different program in the calculator because the calculation that it does needs to be a little different. And so the program you're going to use in these cases is t-interval. So this is when sigma, or the population standard deviation, is not known. And so instead of a z-distribution, which is another word for a normal distribution, we're going to use a t-distribution. To use a t-distribution, we still have to have a simple random sample. We do not know the population standard deviation in this case, although you might be given the sample standard deviation. You do need either the sample to be normally distributed or n over 30. Some random trivia about the t-distribution. This is actually in your book as well, and you can Google it. It was actually developed by a brewer and chemist at the Guinness Brewery in Dublin. He needed to do quality control testing on small samples of beer where he didn't know the population standard deviation. And it turns out that this t-distribution models that much more accurately than a normal distribution would. He was not allowed to publish under his own name, so he used the name student. So a lot of times you'll see this as the student t-distribution. Bear with me as I share my geek moment, but I'm actually recording this video. I'm in Dublin for a conference, and so I went over to the Guinness Brewery and was very excited to see that they even recognized William Gossett at the brewery tour. And so I got a picture next to the plaque that they have for him, and you can see there at the bottom that it's the student t-test. We're working with the student t-distribution, and we'll actually talk about the student t-test in the next chapter. The t-distribution is a really important one. It's different for all different sample sizes, so it's still the basic bell shape, but it can be steeper or shallower depending on the sample standard deviation, whereas with the normal distribution you need to know the whole population standard deviation. Here we can accommodate different standard deviations for each sample, and it will give you wider confidence intervals than a normal distribution would because we're a little more uncertain if we don't know the standard deviation for the whole population. So it'll make them a little wider just to be safe. The flowchart's the same as it was in the last section, just this time when you get down to the bottom you'll choose t-interval instead of z-interval. What students often have trouble with is just deciding when do I use which. So a z-interval can only be used if you know the population standard deviation. A t-interval can be used in cases where you don't know that. You might have a sample standard deviation or you might have no standard deviation at all, just data. So both of these require either a normal distribution or a sample size over 30. T-interval is good for smaller sample sizes if you know it's close to a normal distribution because with smaller samples you often don't have that population standard deviation. But that's going to be the key for you. Do you have a population standard deviation or do you not? So pause the video, read through these three, and see if you can figure out which is which, and then I'll give you the answers. Okay, so on the first one we only have a sample size of 20. That could be a problem, and it is because we are not told that this is a normal distribution. Even though t-interval is, we keep saying they're good for smaller samples, not if we don't know that it's close to a normal distribution. So that is not going to work. We're not going to be able to do that one at all. The second one, we have a sample size of 20, but this time we're told it's a normal distribution, so we're safe. Z-interval is better if we know the population standard deviation. T-interval is better if we don't. Well, reading that, we have a standard deviation for the sample, not for the population. So we're going to need to use t-interval in this case. It's better for small samples when we don't know the population standard deviation. And then the third one, again, sample size of 20, no, it's a normal distribution, so we're safe, but we still need to pick which one, and this time we actually have a population standard deviation given. That means we can use a normal distribution, so we can do a z-interval. That's going to give us a more accurate confidence interval that's a little more precise than t would. And then a couple more, pause and think about those. So with number 4, we have no normal distribution here, but we do have a sample size over 30. It's still a fairly small sample, but it is over 30, so it's safe to use one of these depending on whether we know the population standard deviation or not. And we don't. We have a sample standard deviation, so that means we're going to have to use the t-interval. That one's better when you don't have the population standard deviation. But then on number 5, we do have a population standard deviation, so we can use a z-interval. It'll do a better job since we have that information. So let's calculate some of these. T-intervals in the same place as z-intervals, stat tests. It'll be the one right under the z-interval. And you also still have the data and the stats option. So everything looks pretty similar except it asks for S, which is the sample standard deviation, instead of sigma, which would have been the population standard deviation. Watch out too, because it asks for S instead of sigma, the mean and the standard deviation are in a different order than they were for z-interval. Round-off rule is still the same as well. We're still working with means, so we'll go one past the data if we have the data. If we don't have the data, we'll look for the mean and the standard deviation in the problem and just match the rounding that they used. So here's an example. Study found the body temperatures of 106 healthy adults. We've got a sample mean of 98.20 and a sample standard deviation of 0.62. So let's go ahead and construct a 95% confidence interval. If you want to, you can pause this and try that on your own first. Our point estimate is our sample mean, so point estimate is 98.20. When we go into stat tests and pick the t-interval, because we had sample size over 30, but we did not know the population standard deviation, so t-interval, that comes out to 98.08 and 98.32. So we are 95% confident that the mean body temperature for all healthy adults is between 98.08 and 98.32 degrees, and that is degrees Fahrenheit. So actually it's looking like the average body temperature of 98.6 that we usually hear about is actually a little bit high. Another example, we have a purchasing agent at a bread company and they want to estimate the mean daily usage of rye flour for their bread. So she takes a sample of 14 days, finds the mean usage for those days and the standard deviation. Assume the daily rye flour usage is normally distributed, and then find a 95% confidence interval. So pause and try that. So the point estimate will be the mean from the sample of 14 days, so 173.0 pounds, and 95% confidence interval. Well, first we need to check whether it's a normal distribution. It is, so it doesn't matter that it's only 14 days. It is a normal distribution, so we can continue. Do we know the population standard deviation? No, we do not. We only know a standard deviation from that sample of 14 days. So that tells us that we're going to have to use a t-interval. So go to stat tests, put the information into t-interval, and we come up with 147.0 and 199.0. And you do need the .0s on there because the information in the problem was given with 1 decimal place, which means the original data must have been whole numbers, so the rounding needs to go to that 1 decimal place even though they came out even. So we are 95% confident that the mean daily usage of rye flour for all days is between 147.0 and 199.0 pounds. We have a data option with t-interval as well. It works exactly the same, where you go to stat edit and put the information under one of the lists and then change the stats option in t-interval over to data. So it works pretty much the same as in the last section. So a data example, we have some quiz scores, same as last section, but this time we do not have a population standard deviation to go with it. So we're going to find a 90% confidence interval in this situation. We do not have a population standard deviation given in this case. We are told that it's normal, so the fact that that sample size, there weren't very many quiz scores, but even though the sample size is small, we're okay because it says it's a normal distribution. But this time we do not have a population standard deviation. In fact, for this problem, there's no standard deviation given at all. Well, that's okay because that means the calculator can calculate a sample standard deviation as it goes, but because we don't have one from the population, it's going to have to be a t-interval. So you go to stat edit and you'll put all those quiz scores in. You may still have them from the last video. And then you're going to go to stat tests and go to t-interval, change it to data, and go down to calculate, and the confidence interval will be rounded to 1 decimal place because we're doing the mean and they were all whole numbers, so we'll go out to 1 decimal place. 23.9, 32.5, so we are 90% confident that the mean quiz score for the population of whoever this was is between 23.9 and 32.5 points. And if you look back at the other one was smaller. The t-interval comes out wider, and I kind of mentioned that before, that if you don't have a population standard deviation, you can't be quite as accurate. So it has to go wider to be safer and to be a little more confident that it's actually wide enough to catch the real value. Confidence intervals are very useful by themselves, but they can also be used to compare two data sets. And when we're doing a comparison like that, what we're really looking for is, do the confidence intervals for the two data sets overlap at all? Because if they overlap, then it's possible that the mean could actually be the same. So let's look at an example. So let's look at an example where we have the head breadths from some Egyptian skulls from different time periods, and we want to see if it looks like head sizes have changed over time. So we have a data set from some skulls from 4000 BC, and then we also have some from 150 AD. We're going to assume that it's a normal distribution so that we're able to continue even though the samples are very small, and we're going to do 95% confidence intervals on both so that we can compare them. Since we were not given population standard deviations, we're going to have to use a t-interval, and we're going to have to use t-interval with data. So you can go into stat edit. You can put them both in if you want under L1 and L2. If you do it that way, you'll just have to change, when you go into the t-interval data screen, you'll just have to change the list to L2 for the second one. But you can do both of those with t-interval data. So for the 4000 BC, we end up with a confidence interval of 125.7 to 131.6. And then for the 150 AD group, we have a confidence interval of 130.2 to 136.5. So let's compare those. If you sort of think of mapping them out on a number line, so the 4000 BC goes from 125.7 to 131.6. 150 AD, you have to back up a little bit. It starts back at 130.2 and goes to 136.5. So if you look at that, there's actually a little bit of an overlap. Confidence intervals mean that we think the population mean is somewhere in that interval. So there's an overlap here, which means it's possible that both means could fall right within that overlap. So they could actually be the same. So that means there's no significant difference, no statistically significant difference between the mean head sizes in 4000 BC and 150 AD. Those would have to be completely separate and not overlap at all to have a significant difference between the two.